All right, so our next talk is by Rosario Gonzáles-Férez, and she's going to tell us about polyatomic ultra-long range Rydberg molecules.
So I will start like the rest of the speakers. Thank you, the organizer, Stephen, Hannes, and Hussein for the invitation and for the nice meeting they are doing. But I can quantify my thank you by showing you what is Granada. So, and my happiness to be here and avoid, this was yesterday, and avoid the heat wave that we have in Granada. So I'm going to tell you about the love story between Rydberg atom and polar molecules. And let me start you with some parallel things. Like, we know all what are Rydberg atoms. We have this beautiful picture. Many of us we have almost in our talk. We have these amazing properties. And molecules are complicated. I have worked with all these molecules in a way or another. And in that moment, I could tell you all this complexity and richness that they have, that we have to take into advantage. But having been in UK and having British colleagues that they speak much better than us, I can just borrow the sentence of Simon Cornish from a few weeks ago at the IGAS and say, the flavor of working with molecules is that everything is more complicated. And you could make him happy, and this student from Marcus Arndt group also, and retweet the sentence that was posted during the ICAS conference that Guido Pupillo nicely organized 2 weeks ago in the beautiful Strasbourg. So the idea is like everything we have been saying about Rydberg atoms, it could be done parallel to Rydberg with molecules. And I have only a few examples here. Please forgive me if your name is not included here. Quantum computing, we have yesterday several talks. There are more to come, like from Mark, Misa was talking, and there are more to come about how to use Rydberg atom for quantum computing. The first proposal to do quantum computation with trapped molecules was done already more than 20 years ago, but Dave DeMille, and that was how he was proposing to have this tilted electric field in order to couple the internal states. But 3 years ago already, John Preskill explained us how we could encode the qubit in more complex molecule like symmetric top molecule, and that was towards the same idea. And there have been many, like Peter Zoller have been working there, so there have been many works there. Yesterday, we had another session about quantum sensing here, and I'm only mentioning the chair because I want to get his favor to get some extra minutes. So Jim was giving yesterday a very nice talk about quantum sensing, and there are many works to do with quantum sensing with molecules. For example, here you have 2 reviews from Nick Hutzler and Tanya Selavinsky about several possibilities that they have done about testing fundamental physics. And we all know these 2 groups, I mean, there are many more, but I have highlighted here the studies to measure the electric dipole moment from the ACME collaboration with DeMille, Doyle, and Gabriele. They use thorium oxide, and Eric Cornell and Yunje, they have hafnium fluoride positive. And that was the latest result. They posted last December. And they have the best measurement ever. And in case you are interested, the result is consistent with 0, and it gives an upper bound of 4 times 10 to the minus 13, and it's like 2.4 better than expected. And I could continue with chemical reaction with Rydberg atom and chemical reaction with other molecules, and so on. But I will stop here and then continue where this perfect marriage started. And they started already like 10 years, more than 13 years ago. Hussein and Seth had this great idea of combining the Rydberg atom here with a molecule, and then this anisotropic scattering of the molecule with the dipole moment of the molecule with the Rydberg electron. It creates this kind of electronic structure as a function of the internuclear distance. This is what the experimentalists like to call a spaghetti-like behavior, where the important thing is we have all this oscillation, and they are deep enough to accommodate bound state of this large molecule. And here you see the electronic structure. How does it look like? Here we have the Rydberg core, and here the atomic core, sorry, and here we have the diatomic molecule, where it could point towards the core or weigh the core depending if it is inside or outside of the Rydberg orbit. And then this first study was done for a lambda doublet molecule. So it was really considered to have only 2 states of the molecule. And that was the simplification they were using. But there were much more studies. There were first Susan Yelin and Hussein Sakdepur. They had this study 1 year later, also with Yelena Kuznetsnikova, that they proposed to use quantum gates and addressability to read out the states of the molecule. And they have this structure here where they have several molecules on a Rydberg, on an optical lattice, and they will interact with Rydberg atoms. 1 year later, Guido Pupillo, parallel with Hans-Peter Buchler, they have this idea of atomic reservoir where they propose to use the Rydberg atom to cool down the molecules. There were more. There was another proposal of non-destructive readout also from Susan and Hussein, and that was the same idea, very much control structure where we have the optical lattice for the molecules, and then we have the Rydberg atom on the top of that one. And this idea of non-destructive readout has been very successful applied by Stephen Hogan and also by Christian Koch here, using the idea of an electric field in aviation. This is a much relaxed, so like it's less confined environment because the molecules are not localized in the optical lattice, and the idea is to have this energy transfer to really detect which are the states of the molecule, and they are the states that we're using in both cases. Furthermore, there was a spin effective interaction also from the group we call the Harvard group, with the idea of having they propose to have a spin effective system and code with the Rydberg atom and the molecule. And already 1 year ago, Kang Kwei-Ni and Mike Tarwood, they have another proposal how to use quantum computing, quantum information architecture, combining a Rydberg atom in the center interacting with 2 molecules. So this perfect marriage, how does it look like? We have the Rydberg atom that we describe it as I will describe it as a core with a single electron, and we have to distinguish if they are quantum defect state, the low angular momentum state that they are really see the core, or the hydrogenic-like state that they are highly excited and they, orbital angular momentum large, and then they just see a point-like charge. And then we have this effective Hamiltonian, which will depend this for the Rydberg electron that depends this effective potential depend on the angular momentum. And then we have polar molecules, and I'm going to describe the 2 kinds of polar molecules. I will describe polar molecule like potassium rubidium or rubidium cesium, which is the sigma plus ground state. And I go to this one of the simple approximation I could do, assuming that they are Bohr-Oppenheimer approximation and rigid proton. So I consider that this is the rotational kinetic energy, and I could describe them using the spherical harmonics to describe the rotation. But I also have this kind of molecule, NO or OH, where there's so the ground states are 2 pi, which means we have lambda doubling, and then it's even easier to describe them because I could restrict my description to 2 parity states, opposite parity, and assume that they have only these 2 states, positive and negative parity, and that will be my molecular Hamiltonian. And the idea is that this molecule, what it says, a positive core, and then the Rydberg electron, and they produce an electric field that it will couple with the dipole moment of both systems, depending in which case the coupling might be a little bit different. And what we say is we are in the gas phase, so we go from these free molecules, we include an electric field, and normally what we get is this orientation of the molecule. That will be one of the effects if this electric field is strong enough. So that means the molecular fixed frame is now fixed in the laboratory fixed frame, parallel. It's not parallel, it cannot be completely parallel, but the dipole moment is pointed towards the direction of the electric field. And that is the charge dipole interaction. That will be this is how my system, my molecule look like. I have here the core, the positive core. Here I have the Rydberg electron, I have the diatomic molecule, and then this is the Hamiltonian. So I have this atomic Hamiltonian. Here I have this, doesn't work there. I have here the atomic Hamiltonian, sorry, I have here the atomic Hamiltonian, and then I have the molecular one, I have the interaction, and sometimes we include even the Fermi pseudopotential. So the interaction is, as I said, with the dipole moment, coupled with the electric field produced by the Rydberg core, here by the atomic core, and the Rydberg electron. One of the important limits we have in this system is the Fermi critical dipole moment. So the dipole moment should be smaller than 1.6 divide in order to avoid that the electron is captured by the diatomic molecule. And in some description, we even include the Fermi pseudopotential, the S-wave scattering of the electron with the molecule. So what is the signature of this Rydberg molecule? The first couple that I'm going to consider was suggested by the group of Simon Cornish, that they wanted to see experimentally this Rydberg molecule. So I have rubidium in this manifold. It's that they generate n equal 49 with angular momentum larger than 3, and they wanted to go to this 52s and combine with any rotational excitation, because they are, as Simon always said, they are very, very good climbing up the rotational ladder of the molecule. So they will combine that with rubidium in any rotational excitation, maybe 1 or 2, and that's the rotational constant of rubidium cesium, and this is the dipole moment. So for these manifolds around here, this is how this molecule looks like. This is energy as a function of the internuclear distance of the separation between the core of the diatomic molecule. And when they are very far apart, what we have is just two independent systems. With the energy limit will be the energy of the Rydberg atom with the rotational excitation. And this is what we see here, rubidium in 52s with the ground state of the polar molecule. Again, this 52s with n equal to 1, 50d with n equal to 5, and then n equal to 2, and so on. Then we have here n equal to 3 with 52s, the 49f, and here is the degenerate manifold. And all these states are shifted due to this interaction. And the important thing is we have this oscillation here, and they are deep enough to accommodate bound state. So if they want to go this 2-photon excitation, we will focus on this S state here. And that's what we have here. This is the 52s with 2 rotational excitation with 1 and 0. And we see that all these bound state, they accommodate, all this potential accommodate bound state, and they could create potentially the molecule. So if we look for that one, the point is like they need to have the twister. I mean, they work in optical twisters, so the twister should be separated around 220 nanometers. So that means that we have this scheme where we have here the atomic Rydberg atom, and here the molecule. So the molecule should be inside the atomic orbit. And well, so far they didn't manage to do it. So they only are 300 nanometers, which I think is very good. It was very complicated experiment. So they are in this region. I'm not going to describe anything any longer. They don't have the Rydberg blockade. We observe Rydberg blockade. And I will just tell you, wait for Thursday for Simon talk. But in the meantime, you can also read our focus article, which was appeared last Friday in physics. So the next system, the next couple is cesium combined with rubidium cesium. And that was actually inspired by the work of Johannes and Jim, because cesium is have this peculiar quantum defect, which is the S state is approximately 4, and that gave them the possibility to observe this trilobite state exciting to a S state. So now I'm going to go to the 70 citation of cesium, always keeping in mind that this is what I would like the experimentalists to do. This is the electronic structure of cesium Rydberg state, and I have again the same rotational constant and dipole moment for the molecule. And if I go there, this is the electronic structure in gigahertz as a function of nanometer. Now you see that the scale is larger because we are rotationally excited more. And then it's a little bit simple, the spectrum, because we are higher in the spectrum of the electronic atom, so like the Rydberg electron. And we have here the signature, which is in the cycle, which is giving us some non-adiabatic effect. This avoided crossing, what we have done is to solve this bound state in that region, what you see here. And this is when we including the coupling between the upper and lower potential. This is non-adiabatic coupling. This is all of the states I will get. And in order to see which state are bound, we do this a method that stabilization method that we in our theory, what we move is the lower limit of the box we use to solve the time independent Schrödinger equation. And these are these bound states as a function of this lower limit here that we use for our integration. And then you see there are some lines that they keep constant while other not. And those that they keep constant correspond to the truly bound state. So that will be the bound spectrum, the vibrational bound spectrum of my Rydberg molecule. And for this bound state, we have computed what is the contribution of the orbital angular momentum of the Rydberg electron to this bound state. And this is what you see here. The red one is S, the blue one is F character, and in green, sorry, is the rest. We consider only we take into account the S and the F, because we have here the S state and we have an avoided crossing from the F state. So we wanted to see what is the mixture. And what we see is that essentially the S character from this avoided crossing is dominating to the states around this region. So the higher excited state and the lower one from the upper potential that you see, and the rest are very much mixed with all partial wave due to this electronic structure here. And then we see that the dipole moment as a function of this bound state here, we see also that this is large dipole moment, and we also see like this is decreasing because of this dominance of the S state here, and that will be in the lower potential, and in the upper potential we see this oscillatory behavior depending also on which state are populated. So we have another couple, and that's we are working with Stephen on that system, and we combine now helium with HT3 and NT3, sorry. And I am plotting here again as a function of the internuclear separation now in atomic units, the potential energy curve for n equal 55, that should be here. And this HD3 is also a lambda tablet, so I could also describe like a two-state model. And we have all this rich structure where they have many bonds, many oscillatory behavior where they could accommodate bound state. These are the constant. This is the splitting is 1.6 gigahertz, and the dipole one is 1.5. And if I zoom in that region, we see that they are bound state. There's a significant bound, a large amount of bound state, and they are well separated in a spectrum, which means that the experimentalists could distinguish them experimentally due to this energy splitting. And we have analyzed this energy splitting as a function of the internuclear separation for this state coming from MP. So this is from approximately N20 to 40, and then we have this gap where this is the last state I was showing you, the 55 P, and then we see that this decrease significant. I mean, as is normal as increasing the excitation of the Rydberg electron, but important is that this is all of them. They are large enough separation that they could be distinguished experimentally. And I always get the question is how this state changed when I change the properties of the molecule. So what we have taken the n equal 20, helium in n equal 20, I have can convert, this is how they will look like. And I have focused in this state, which is coming from 20s. This is this two state depending on the parity of HT3. And we have changed two things. We have changed the molecule splitting. So that will be changing the separation between the lambda doublet states, and what we see just there, and this is the two states here, we see just they are shifted as we increase upwards. In black is the HT3 case, so that nothing really changed significantly except the separation between these two curves. But if I change the dipole moment, we see that the potential really changed. This will be going to higher dipole moment, that will be to smaller dipole moment. And then we have computed how many bound state do we have it. So below 0.6 divide, we will not have a bound state any longer. And the binding energy increase as a function of this dipole moment. In red is the real molecule. And then here we have highlight this Fermi limit, which will not surpass, but then we have continued to see how does it increase. So this is really the binding energy that many, I mean, even for larger and smaller dipole moment we have found state. The last molecule I'm going to talk to you is this negative Rydberg molecule. This is still unfound, called the molecule like that one. This is NO in an excited state. NO is a very steady molecule because it's a neurotransmitter. We need it in our body, but if we have too much, then it becomes poison. It's really amazing the amount of results that we could find on NO. This is the electronic structure as a function of the internuclear distance. And we are working with this ground state here, and one of the rotation of one of the Rydberg states over here. For the Rydberg state, we use Tennyson calculation for computing the quantum defect state and to describe the Rydberg wave function. And for the ground state, we have again the advantage. This is a lambda doublet molecule. So we only take into account these two last bound states. We have here the splitting, which is not too, it's a small, and that takes an advantage because the dipole moment is really, really small. And that's how the electronic structure look like as a function of the internuclear distance when we go to n equal 40 and we gain seeing all these bounds, all these states with many with oscillatory behavior. We also see many blue shifted states as before. And the advantage is if we look here, if we look for the 40G, which is here, coming from that one, and these two states that they come from the 40F, they all have bound state and they could accommodate this, the vibrational level. The disadvantage here is that the experiment is going to be done by Harald, whereas Harald was somewhere here, Harald is there. And the point is like, this is not in an ultra cold sample, it's in a cell sample. So at least they will be able to see this pressure bonding like it was observed before. And for that one, I really suggest that you see Harald Kluber talk on Friday. And I would like to conclude giving you some preliminary results about how to create these quantum gates with resonance enhancement for rubidium with rubidium cesium. So if we excite rubidium to 101D and 102P with the ground state molecule, with the rotational ground state molecule, this is the structure as we see as expansion of the internuclear distance. And when we leave this the electronic orbit, the Rydberg orbit, we see this exponentially behavior approaching the dissociation limit. And if we focus more or less around that region, we see that the shift is very small. This is given in megahertz. We now go to a resonant case where we take the same 101D combined with rotational excitation with the n equal 1, rotational excitation n equal 1, and the P state, 102P state with n equal to 2. At large internuclear separation, we see that the coupling, the energy splitting is very small. And then we have this resonant coupling about the state. The behavior of the curve has changed significantly. We don't have any longer this exponential approach to the limit. We have fitted, and depending on the curve, we have a power law like like to the r to the power of -3, -4, depending when you approach. And the important part, and this is for you, Stuart, sorry, I was almost close to call you Charles again. Sorry, this is, if we look here around 1.5 micron, they are really a curve that they are split like 2 orders of magnitude compared to this case where the shift is almost 0. So we are working on that one, we are analyzing that one. Unfortunately, we did all these studies for the 100 one, and Simon is going to use another state, so we have to repeat the full study. And with that one, I would like to conclude this perfect marriage between molecules and Rydberg atoms. For that one, I have shown you some signature of Rydberg molecule, how to create bonds, how to observe Rydberg blockade, that's you have to wait until Thursday. Non-adiabatic coupling, and also these negative molecules that they could be created in the vapor salt. And we are working now to how to do these quantum gates with resonance enhancement. And to conclude, I'm not alone, of course. This work has been done in collaboration with Hussein, Taktefur, Janine Setzer, Pablo Fernandez Mayo, Juan Manuel García Garrido, and David Mellado Alcedo. They are my student. David already graduated and he moved to Córdoba. And we are working with different experimental groups with Canquen. We are working to see if they can observe the rubidium KRB rubidium system is Simon Cornish and Stuart Adams, and then Stephen Hogan for the helium ND3, and I think they are also going to work helium NO, and the Rydberg negative molecule with Tillman Fau and Harald Gruber. And with that one, I thank you for your attention.
This primary critical dipole, you think this matters in these cases? I mean, again, some has to do with the binding energy of the electron to the polar molecule compared to the binding energy of the electron to the Rydberg.
Like the 1.6, what I have seen, and I was doing some calculations with Seth and Hussein, is that we increase it a lot the dipole, we don't get converged results, because the higher is the dipole numerically. So it doesn't mean that the electron is really going to be catched by the molecule, but then the system becomes a non-possibility to do it. And numerically, we really see that we have to include like neighboring manifolds and neighboring manifolds, and the result doesn't really converge because of the strength of the, but that will be a theoretical problem, which I don't know what will happen in the or computational problem.
So why is it that in the video where we have different complexes, higher rotation space and more
in Rubidium system, the point is that you have one moment. Let me go back. Now I have two of this, and I don't know what is it. The point is that like the S state, like when I combine this, this is a very much isolated state with n equal to 0. And then the point is like this one is closer to the manifold, also gets some influence, and also how the wave function look like. And this is significant. I mean, this is a special case which is significantly affected by the manifold. And then the closer up to the manifold, then they have, I mean, the important is how much of the Rydberg wave function you get mixed with other states. And the closer they are, the more they are mixed, and then you have the deeper ones. That's why this is significantly deeper than the rest.
I have a quick question. So in the NO molecule,
Yeah.
what's that?
Yeah.
Well, I guess with these potentials that you calculated, they're very like symmetric up and down. Is there? Maybe it's not that one. It's the last. Maybe it was on your last one.
That was the helium. This the helium.
Oh, okay, maybe that's it.
Here you have this, and also the other one. No, that's I know what you mean. The very symmetric is this one.
Yeah, that one. So
That,
oh, that one. Sorry. What's the mechanism for that? That should be something like that's basically mechanical or something.
it's a really coupling between this is a really coupling between these two states, and then it's really symmetric. We have seen that it's really like a two-state model where you have this correspondence with this one will be correspond with that one, and this is where you see this state. So it could be really considered as a two-state model partially, not completely. And this all this upcoming are mainly dominated by this state with the Rydberg, and the lower one are mainly dominated by the P state. But when we do the coupling, for example, we see that the coupling, I mean, not the coupling, the fitting to see how this exponential behavior is, they have the same behavior. So this curve compared to that one and so on.
I mean, I guess like, what's the difference between, I mean, I guess you're, in the simplest case, right, it's still the electron interacting with the dipole on RBCS, but why, is there like a reason of like the quantum numbers of the orientations of why one's repulsive and one's attractive?
It's essentially the fact that you, I mean, you have the molecule sees an electric field, and depending how this electric field, they are shifted upwards and downwards. And then due to this coupling, you see this upwards and downwards electron. Because it's not always a positive or negative field that the molecules see.
Let's thank Rosario.